Glad you're here.
Thank
So
you.
Jeff, in a second, I'm just gonna switch. My computer's working again. This is the school computer now. And I'm gonna switch to my screen and then I can work through one of the problems for you. So you're talking about part C.
No, I was on part B because I was just having,
Okay,
like
no
I was
problem.
just getting stuck on it.
Yeah. So just so you know, like some people are done with the lab and good for them. And they were persistent. They jumped in and it worked for them. And there's other people who are, stuck at part B or C and it's all good. And there's some people who haven't even started, which I'm worried about. But wherever you are, it's totally fine. And I will definitely work through a problem like that. Hi, Jordan. How are you?
I'm doing pretty good.
Good. I'm glad you're here.
Are
Okay.
we just about to get into part B? Because I think that's the one I'm on too.
Oh, perfect. Yes, we are.
I did have one. The lab is due tomorrow.
Well, it's been, it's tomorrow the 24th? Yeah, it is. It's fine. We're just all doing the best we can. We're trying to catch up. If I need to move that due date, I can do that.
Okay.
Yeah. Hi, Ethan. How are you?
Doing good. How you doing?
I'm doing good. My computer's working, so that's really exciting. I'm just about to screen share and do a part B from the lab. That's where we're starting today.
Okay.
Okay. So we have a mass. Oops. And the mass is for oxalic acid dihydrate. And the molar mass for this is 126.08 grams per mole. Okay. And so for our mass, the initial mass is 33.342 grams. And the final mass is 33.222 grams. And what happened was somebody had a test tube that had about about 1 gram of this stuff, and they massed it on a beaker on a balance. And then into a flask, they were tapping until they had put about 0.1 grams in. And then they remassed what was on the balance. And the stuff that landed in here is just the difference between those two weights or masses. And so we have 0.120 grams of oxalic acid dihydrate in the flask. And then dispensed from the burette was the sodium hydroxide. And we don't know the concentration of sodium hydroxide yet. The goal in part B is to figure out what the concentration is. The initial burette reading was 0.10 milliliters. And then it was put into this flask here. So we had the oxalic acid dihydrate, we added some water, the oxalic acid dissolved. Looks like the flask dissolved. So it's floating around in there. And we're gonna add to this acid base until the indicator goes from colorless to just barely pink. And when it does that, it's 17.70 milliliters. So we're looking at the base that has been dispensed, the change in volume. And we're going to use that information plus the mass of acid. And we understand that when we were done, the moles of acid matched the moles of base, but not exactly. Actually, let me say that differently. The moles of hydrogen ion that reacted are equal to the moles of hydroxide. When that happens, we say that's the equivalence point, and hopefully we. And when we stop titrating, because we notice that's the end point. And when the equivalence point and the end point are the same, that's a really great titration. Okay, so I'm going to jump in with some calculations. Let me just erase this.
I had a quick question.
Yes, what's your question?
Is this with both part Bs? Because there's part B for standardization of the NaOH solution, and there's also one that's molarity of base.
Those are the same thing.
Okay.
So the sodium hydroxide solution, I'm glad you're talking to me. Thank you very much. The sodium hydroxide solution is the base, and standardizing is a fancy way of saying we're going to do this process to figure out what the concentration is.
Okay.
Yeah, so that's what we're doing in part B. Okay, so this is going to be my roadmap. I'm going to start with, my goal is to get the molarity of the base. And molarity is moles of base per liter of base of solution. Okay, so we're trying to figure out what that is. We're going to start with a balanced chemical equation, and then we're going to go use our grams of acid and its molar mass, 126.08 grams per mole, to get to the moles of acid. And then the balanced chemical equation to get to moles of base. And once we get to moles of base, if we divide by, once we get to moles of base, if we divide by the liter of solution that it's in, that's the molarity. And so we're going to divide by the volume, but the volume needs to be in liters. And that's the stuff that came out of the burette. Okay, so here I have 0.120 grams of oxalic acid dihydrate. That's this whole business here. That's a lot to write, so I'm just going to write acid. And then we have the molar mass, 126.08 grams per mole. I want complete units, so I'm going to remind myself it's the acid. And now I need a balanced equation. So from the pre-lab, you took oxalic acid, I think this was 1A, and you're adding it to sodium hydroxide. And the goal is to make water and sodium oxalate. Oxalate's a -2, so it takes 2 sodiums. So this acid is called diprotic, and that means it has 2 protons that are acidic, 2 protons that can react in an acid-base reaction. And this base just has 1 hydroxide. But if I had 2 sodium hydroxides, it could react with those 2 acidic hydrogens to make 2 waters. And so the first hydrogen comes from the acid, and the second hydrogen is part of a hydroxide that comes from the base. So when we do acid-base reactions, neutralization reactions, which is one of 2 kinds of double displacement reactions, sometimes I write water this funny way. It's just to remind myself that the hydrogens have a different origin. One came from the acid, the other is part of a hydroxide. Okay, so I see 1 mole of acid, requires 2 moles of base. And that's what I'm going to use in my equation here. 1 mole of acid, oxalic acid. It was a dihydrate, but when it's in solution, the water's floated away. And the base is the sodium hydroxide. Okay, and all of that was contained in the difference between 0.1 mils and 17.7. So our difference in volume is final minus initial. And so my answer is 17.60, 4 sig figs. Both of these go 2 past the decimal, so my answer goes 2 past the decimal. And which solution is it? It was the solution that came out of the burette. Now I do have one little problem. Okay, so the grams of acid cancels, the moles of acid cancels, the moles of base doesn't, and it's over milliliters, but molarity is moles per liter. So I'm gonna need to change my milliliters into liters. There's a couple ways I can do that, but this is the way I'm gonna do here. I'm gonna say times 10 to the -3 liters, because 10 to the -3 is milli. And so this whole thing here means milliliter. So go ahead and do that on your calculator and see what you get. So my calculator gives me a lot of digits, and I want to keep track of all those digits. Eventually I would round, excuse me, my sig figs to 3, and it would be 3 because when I subtracted my masses, I ended up with 3 sig figs for the mass of acid. And my other piece of data is 4 sig figs for the change in volume of base. So the answer should have 3 sig figs, but I'm not going to round because I don't want to introduce rounding error. And that has been a big problem for some students in this lab. So in the box where you write what's going on, you might write this whole answer, but make sure that you underline it so that I know you know where you would have rounded for reporting the answer. The reason you're going to keep all of that is so you calculate a mean that's accurate, doesn't have any rounding error, and you get a mean deviation that's accurate, doesn't have any rounding error. Questions?
Is that in the notes and example calculations box you're talking about?
Yes.
I have a question. When you get the mean of the molarities, do you use the unrounded values,
Yes.
correct? Okay.
So when you get the mean, I'm going to tell you what the answer is, but I'm still going to check your work. I know what all the answers need to be. So if trial 1 is right and the mean is right, but 2, 3, and 4 aren't right, I'll know that something fishy is going on. But I'm going to tell you what the mean is. The mean is 0.109476318. And that's a lot of digits. You don't actually need all those digits. That is the average molarity of the hydroxide. But you do need to carry a couple extra digits. So let's say that you end up with this answer and you need to go on to part C. You want to carry some extra digits so that in part C, when you use this average molarity to answer the question for part C, you don't have rounding error. Because if you do, I'll kick it back at you. That sounds bad. I'll hand it back so you can redo it for more points.
And I have a question for part D. We use the mean value molarity for the calculations, for every calculation for that?
Yep.
Okay.
Yep. So every calculation in C and D is going to need this number.
Okay.
Yep. Okay, are there other questions about part D?
Yeah, maybe one for part D. When we get the mean percentage, do we also use the unrounded values when we're getting the mean for that, right?
For both C and D.
Okay.
Okay. So I'm guessing there could be somebody here who would like to see a calculation for part C. Is that true? I don't want to waste your time, but if it would be helpful, I would be happy to do it.
Yeah. Let's see. Which one was it? It was the mean deviation for part C.
Okay, let me do the first, like how to calculate the thing, and then we can talk about mean deviation. So mean deviation for part B and part C are the same idea, right?
Yeah, so I think I just figured out what I did wrong, what you just said. It was, so you use the mean average for all the calculations for part C, right?
Yes.
So I think what I did was, so for trial 1, I took the trial 1 molarity from part B and used that.
Some students did that, but that's not right.
Okay.
And if you think about it, it doesn't seem right, does it?
No.
Like, the point of doing 5 trials was to come up with the best, most reliable molarity, the best answer, and then use that best answer going forward. But you're not alone. Other students did that too.
I see. So I think I just see what I did.
Yeah.
That should probably fix my mean deviation then, right? Because I'm pretty sure I did the calculations for the deviation correct, at least.
Yeah. So you come up with a mean, and I'm looking at part B again here just to talk about what a mean deviation is before we move forward.
Okay.
So for the mean, I come up with something like this. And I have complete units because I want full credit and I want to build good habits as a scientist. I don't want to have to go back and fix bad habits later. Okay, so that's a mean. To find the mean deviation, so the bar over the D means average, mean, and the D stands for deviation. To find the mean deviation, I'm going to have to take molarity 1 minus the average, the unrounded average, and I need it to be positive. And then I'm going to do that with molarity 2, molarity 3, molarity 4. And there's a way to write that in kind of shorthand notation, so I'm going to do that. I'm going to change my 1 here to an X or an I, and then I'm going to put sum here. So this is me summing all the positive deviations. So the deviations, some are positive and some are negative, and if you add them all together, they should add to 0. Because the whole point is, in here in the great scheme of some number line, this is the average. And maybe value 1 was a little higher than the average, but value 2 was lower than the average. Value 3 was lower, but value 4 was higher, and value 5 was higher. So if we added together all the how much lower those 2 trials were and how much higher these 3 trials were, we should get 0. That because this is how much do things differ from the average. Where did the average come from? From those 5 values. So if we were to just sum the deviations, they would equal 0 if we didn't have any rounding error. And so that's why I have the absolute value bars here, is because what I need is to take the deviations that were on the left of the arrow and make them positive. I'm going to get rid of this one here and put it over here, and get rid of this one here and put it over here, and then I'm going to sum all of these. That's what I'm doing here. I'm not done though, because the next thing I need to do, if it's going to be an average deviation, I need to divide by the number. And if X was 5 values, I divide by 5. If my units for molarity were molarity, my units for deviation are also going to be molar. And molarity and molar are interchangeable. It's like, do you say was or were? You know, it's one of those tense sort of ideas. It's not tense. You know what I mean? It's molarity and molar are the right word. And do you add the ity? Depends on the context. Okay, so that's a deviation. And then once we've summed our deviations, we can find the percent uncertainty. By taking that mean deviation, and again, even though I rounded it to the proper number of sig figs, which is probably going to be 1 or 2, I'm not going to use that rounded digit. Okay, so in part, let's see, in part C, for example, the mean deviation has 2 sig figs, and it should. But when I take it and move forward with it, I'm going to use the unrounded value because I don't want to have rounding error. So I'm going to take whatever this deviation was here and use it there. And then whatever this molarity was here and use it here. Unrounded times 100%. And that's a percent uncertainty. So for the molarity, we know it has 3 sig figs because of the mass. The mass in part B led to a molarity of sodium hydroxide from part B that was good to 3 sig figs. We're carrying extra, but when we finally round and report an answer, we're going to round to 3. The deviation, however, is going to have fewer sig figs. So for part B, it's going to have 1 sig fig. And it just has to do with the math. And at this point, if you want to understand that better, we can talk about it, but I don't think the whole group really wants to. And I don't want to spend time at this moment. But once we're done, if you want to stay and I'll walk through the calculations, I can do that for you. And that would be a good thing to do, but sometimes we're just tired and we just need to be done. I get that. So my percent uncertainty sig figs are going to be the same as my average deviation sig figs. And we're probably going to lose sig figs because there's a subtraction step to find a deviation, and we lose on the left when we subtract. Okay, so we're almost there. The one last thing we need to do is something we learned how to do early in the class, and that is standard deviation. We have to take the sum of the deviations squared, divide by the number of trials minus 1, because we don't have all the ones in the world, we just have a sample set. Why the minus 1? Because it's a sample set. Sometimes students Google it and they're like, no, wrong, Sue, you're wrong. I looked it up and it said n, and I think there's a subtlety you don't know. If I had every value in the world, I could use n. But if I just have a subset of those values for a particular thing, it has to be n minus 1. And then we square root. And so here we have squared and here we have square rooted. That's why we don't need to do anything absolute value wise, because that's a different way of kind of making all the values positive. Okay, so those are the 4 kinds of calculations we're going to be doing. We're going to be doing a mean, and then we use those means and the values that made them to get the deviation, the average deviation. Then we use that average deviation and the mean to get the percent uncertainty. And then finally, we're going to go old school back to a standard deviation, something we learned the first lab in the class.
For the standard
Sorry?
For the in step 4, the D, is that going to be the same one we found in step 2?
It
It's
is.
like the,
Well,
okay.
yes, it is, but then you're going to square them. Same D's though.
Okay.
And the deviation is just how far does this deviate from the average? Is it higher than the average or is it lower than the average? Good question. Okay, so any more questions on part B or these typical calculations? Because we're going to do all these same calculations in part C with the percent of acid in a mixture, and part D with the percent of acid in a different mixture called vinegar. Okay, I'm going to erase this page and I'm going to talk about part C for a minute. Unless there's something super important, if you're like, Sue, just answer this one question, then I can leave. I will respect your time and I'm happy to do that. Okay, so in part C, what you have is a percent of an acid, a monoprotic acid, KHP, potassium hydrogen phthalate. It's technically a salt, but it has one acidic hydrogen in a mixture. And if we were on the ground, every student would have their own mixture. We have like 300 test tubes of this stuff. And so everybody would get their own mixture and it would have a percent KHP between 20 and 70%. But we can't do that because we're online. And then you would take your test tube and you would say, here's my test tube of unknown they gave me, and it has some of this solid in it. And the solid is made of the thing that behaves as an acid and something inert, maybe sodium chloride. And my goal is to figure out what percent is acid in that mixture. And then you would tap a small amount, 0.2 grams, mass by difference, into a flask. That's meant to be a flask. You would add water, it would dissolve, you'd add phenolphthalein, which is the indicator, and then you would titrate. And your goal is to figure out if 0.2 grams takes whatever volume, how many grams do I have to use to get to 20 to 25 mils? Because a good titration is going to require 20 mils for reasons that have to do with relative error, which is a subtlety that's super important. And I'd be happy to talk with anybody about it. And it is something you should know in Chem 1A, but I don't think today is the day to have that conversation necessarily. Okay, so what we're doing here is called determining sample size. You don't have to do that because your samples have already been done for you. But in theory, if I put 0.2 grams of acid in this flask, and this only required 10 mils, what that means is for you, particular student, you're going to use 0.4 grams approximately so you can have 20 mils. So it's a simple calculation to figure how do I scale up this expensive unknown so that I am always going to require about 20 mils of titrant. And titrant is a fancy word for whatever's in the burette. Why 20 mils? To lower the amount of relative error. Okay. So let's say that you've done that and then you're given some data, and the data is this. Do you see how happy I am that you're here? I am working through your sample calculation for part C, and you're welcome. Okay, so initial mass, once you get to your actual trials, not the determination of sample size, which you aren't going to do, is 26.694 grams. And then the final mass in that test tube, once you tap out a good sample, is 26.162 grams. And what you have is grams of mixture. It's not just acid. It's acid plus something inert. And that ends up being 0.532 grams. This is for trial 1. And then you mix it with water, add indicator, and then you set up your burettes and you start titrating. And your initial volume is 3.6 mils. And your final volume is 21.10 mils. And the difference in volume is 17.50 mils. What do you have in the burette? That's a question, it's not rhetorical.
Is it the NaOH solution?
It is. You know what the concentration of it is?
Is it the 0.109476?
Mm-hmm. Yep. Good. Okay, so now you're going to titrate, and your goal is to figure out how many grams of KHP are in this sample that is 0.522 grams of a mixture. So to get to acid, grams of acid, we need moles of acid. So I'm going to work backwards here. Acid, KHP. I can get there from moles of acid. How do I get to moles of acid? From moles of base. What do I need to do that? Balanced chemical equation, which is part of your pre-lab. To get to the moles of base, I'm going to know the volume of base required and the molarity of base required. And volume is in liters, and molarity is in moles per liter. And when I do that, I get moles of base. And then for moles of base, I can find moles of acid with my balanced equation, which is KHP plus sodium hydroxide, reactive form water, and potassium sodium phthalate, or sodium potassium phthalate. And you can write P, or you can write the CaH4O4, whatever. Okay, so there's my roadmap. Here I go. I used 17.50 milliliters of base that was in the burette. The molarity of that base was 0.109, but I'm going to keep extra digits because I don't want rounding error, because I want to do this once. I don't want to get it back from Stu. And then the capital M here means moles per liter. Moles of what? Sodium hydroxide in this case. But instead of liters, because I'm going to need the milliliters to cancel, I'm going to rename it as 1,000 milliliters in the liter. Because now my milliliters will cancel. Okay. So I've gone from volume times molarity, and the milliliters cancel, and I have moles of sodium hydroxide. So now I'm going to use the balanced equation to get from moles of base to moles of acid. One mole of base is required because of this one you can't see for every 1 mole of acid. Now I'll use the molar mass to get to grams of acid, to get to grams of KHP. What's the molar mass for KHP?
$204.23 grams.
Per mole. Grams per mole. Grams is not a unit for molar mass, but grams per mole is. And I think some of you probably lost points on the pre-lab about that. Okay, good. So when I've done this, KHP, I will have the number of grams for sample 1, and it'll be good to 3 sig figs, but I'm going to carry extra. So go ahead and calculate that. Are there any questions about the roadmap at the bottom? Because I'm about to erase that.
No, no questions.
Thank you. What did you get?
You get 0.391271097.8.
0.3912710.
Yeah, 10978.
I got something a little bit different for that. I got 0.391269961.
Okay, it's okay because tenths, hundredths, thousandths, 10,000ths agree. And actually the 100,000s agree. 69 and 71 are pretty much the same. So we're
Okay.
good. Okay, so what was that? That was grams of KHP that were in that 0.532 grams of mixture. If you multiply that by 100%, that is percent KHP.
And how many sig figs did you want our percent to be?
In this case, it's, oh, just let me finish what I got here, and then I will do that. I got 73.54338. And this value has 4 sig figs. This value has 3 sig figs. This is unlimited. And this is 5. So the smallest value there is 3. So this is 3 sig figs divided by 3 sig figs times unlimited sig figs. This is only good to the 10th place. But I'm going to keep the extra digits and just underline it to tell the grader I know I should round there, because you need the extra digits for the subsequent calculations. Mean deviation, percent uncertainty, etc.
Okay.
Good question. Okay, so that's part C. Any questions on that? Hi, Courtney.
Hi, Sue.
We're just going over the lab. We've done some part B calculations and part C calculations. Does anybody want to see part D?
I would. I'm working on part D right now.
Okay, let me do it for you. So in part D, we're going to set up our burette and we're putting our sodium hydroxide in it, just like we did in part B and C. So we didn't have to clean out our burette. We could just go from one titration to the next. And the thing that we're checking now is for vinegar. Vinegar is a mixture that is mostly water. But in vinegar, there is some acetic acid. Acetic acid, ic acids come from ates. Acetate is C2H3O2, which is something you should all know just by heart at this point. But I recognize that because we're online, it's really easy just to have that table next to you. But this is the correct way to do it. And if students are writing it this way, I know that they're Googling because we haven't learned that in our class. Don't do that. Okay, ic acids come from ates. How many hydrogens do I need to make this an acid? Just 1, and then I hide that charge. But sometimes acetic acid is a very common weak acid. It's like the poster child for weak acids. And so in chemistry, we can represent a weak acid by writing HA. And if it was a diprotic acid, like hydrogen sulfide, which is a weak acid, we would write H2A. Everybody knows that. That's just a common abbreviation. But because acetic acid is so common, we abbreviate it this way, HAC. And so I'm going to do that because it's easier than writing HC2H3O2 every time. Okay, so the problem with vinegar is it is too concentrated in acetic acid for us to get a sample in here that only requires 1 burette's worth of stuff. And so we do something called a dilution. We're going to dilute it in a way that is very predictable. We're going to take basically 1 ml of vinegar and add 9 mils of water, so a 1 in 10 dilution. And then that more diluted vinegar, we can titrate. And so the first step is to do a dilution. To make sure the students have enough acetic acid when we're actually on grams, we say take 25 mils of real vinegar and put it into, and use this special tool called a volumetric pipette that you fill to the mark, and then you can dispense. And it only holds 1 volume, and that volume is 25.00 mils. So it's a piece of precision glassware the students have to learn how to use. And this is why this lab typically takes 3 weeks when we're on the ground, because students make mistakes and it takes time to learn. And I'm so sorry you don't get that opportunity to learn, because you'll have to pay for that later. Eventually you'll have to learn how to do this. Okay, and then we're going to put it into something called a volumetric flask, which is a specialized piece of glassware that is only good for one volume. And the one we would give you would be a 250 ml volumetric flask. And so if we take 25 mils and we put it in 250 mils, that's a 1 in 10 dilution. Once we come up with our concentration of acetic acid at the end, we have to remember the vinegar was really 10 times stronger. And so that's the last step we do, where we take concentration 1 times volume 1 equals concentration 2 times volume 2. This is a dilution equation. And so that is in your write-up. Anyway, then once we have our mixture, we use the same pipette, but this time we're sucking out the diluted solution and we put it into a flask. And then we titrate. And so because we're using this piece of precision glassware to fill our flask, the volume of acetic acid sample, which is diluted, is always the same, 25.00 mils. What's going to change is the amount of sodium hydroxide that we need, but it shouldn't change very much. So that's the setup for the lab, and now I'm going to talk about how to do the calculations. Okay, so our goal is to find the percent acetic acid and vinegar, which is going to be the grams of acetic acid divided by the milliliters of vinegar times 100%. Well, we know what the mils of vinegar are. We already said every time we do this, we're going to use 25.00 mils. So we know what that number is. What we're solving for with our titration is how many grams of acetic acid. So that's the goal. And our starting point is going to be the volume of base times the molarity of base. The base dispensed from the burette gives us moles of base. And if we know moles of base, we can get to moles of acid. How do we do that? With a balanced equation. So here was another part of your pre-lab. Take the equation for acetic acid and add sodium hydroxide to it. Acid plus base makes water plus salt. 1 hydrogen in the acid, 1 hydroxide in the base means we're going to make 1 molecule of water. It's a 1-to-1 ratio. And the salt is going to be sodium acetate. Okay, so our balanced equation tells us 1 mole of base requires or reacts with 1 mole of acid. Can we get from moles of acid to grams of acid? Yes, because we can calculate the molar mass for acetic acid. Questions? Okay, I'm getting sick of blue. I'm going to pick a different color. So the initial burette reading was 3.45 grams, milliliters. And the final reading was 33.05 milliliters. So go ahead and start with that difference in volume as your starting place and use the molarity we got from part B and go from there. I'll give you a minute to do that. Since I can't see your faces, I don't know how far along you are. So if you could tell me in chat once you've got a number and answer, or if you have a question, let me know. You can either speak or do it through chat.
Do you just want to know the milliliter of NaOH?
Sure, we can start there.
So I got, for the first trial, I got 29.60 milliliters.
Okay. Do we have somebody to confirm that? Only Deanna's here today. I will confirm it. Let me look. Hey, I got that too. Good.
Okay, cool.
Okay, and that was milliliters of acetic acid, or no, sodium hydroxide solution, because that came from the burette. Okay, what was the molarity again?
0.109476.
Perfect. Good to 3 sig figs. I'll underline that. And then the units molar are moles per liter. And then it's moles of sodium hydroxide. The liters, I'm going to change to 1,000 milliliters. Good. So now I'm here. You are here. I use my balanced equation, the 1-to-1 ratio, to get to moles of acid. And then I need a molar mass to get to grams of acetic acid. So I just need to add up all those pieces. 1 hydrogen, 2 carbons, 3 hydrogens, 2 oxygens. So I have no idea if I'm going too fast, too slow, if my melodic voice has put you to sleep, or if you're playing video games and muted. I don't know what, how fast to go. Can somebody talk to me? Besides Deanna, who's doing a great job, by the way.
I was going to say you're going at a perfect speed.
I'm
Yes,
like,
This is working.
it's good, yeah.
Okay, good. So we probably have a number now. What's that number?
I got 0.1945914.
1945914.
Yeah.
What you said? Okay, what are my units?
Grams of acetic acid.
Perfect. And then how many sig figs?
Is it 4 sig figs?
No, but thank you for playing.
Okay.
Anybody? And Deanna, I really appreciate you talking to me. But somebody else, I want you all to look. How many sig figs do you think it should be? Oh, here, let me show you. 4 sig figs, 3 sig figs, unlimited sig figs. What's 3 sig figs? Unlimited and 4. So I can say 3. These are questions, like I'm just walking you through the series of questions that all of you are going to learn, should learn, just ask yourself. So I'm not trying to give Deanna a hard time, and I appreciate that she's responding, but these are questions we need to know. So I'm not rounding, but I am going to underline that. Okay, good. Are we done? Is that our answer? Do we put that in the box? No. What we found is grams of acetic acid, and what we're looking for is percent in vinegar. And so we need to do this business and then take care of the dilution that we did. So I'm going to take those grams of acetic acid, complete units, underline, keep track of my sig figs, divide by the milliliters of vinegar, but it was the diluted vinegar. And if it's a percent, if we're making a percent, we always multiply by 1 in the form of 100 over 100. And then the over 100, we call percent. So 3 sig figs, but unrounded, divided by 4 sig figs times unlimited sig figs. Our answer should have 3. What did you get? Tell you what I got. 7.78362. Oh, no, I didn't. I got 0.778362. But that was the diluted solution. And so now I have to do that, take care of the factor that I diluted. Okay, so the volume, the concentration 2 is the concentration, the grams over the milliliters, and the milliliters were 25 milliliters. But that was actually in 250 milliliters of solution. Sorry about this. This is confusing. What I started with was a 25 milliliter sample of the good stuff, the concentrated stuff. And then I made it dilute and figured out what the concentration was. Does that make sense? And the answer is 7.78%, and it was grams of one thing and milliliters of everything. And here's my first value, rounded to 3 sig figs, but I'm not going to use the rounded value for the rest of the calculations because I don't want to have rounding error.
Thank you. That makes sense.
Hi, Jolie. Thank you for talking to me. I'm glad it made sense.
I totally forgot that there was 3 sig figs in the molarity, and so I did 4. So now I've got to. But luckily, I carried over all the decimals through everything else, so there shouldn't be anything but just making sure that I check my sig figs in the final answers.
Right. Have you turned it in yet?
I have, but I'm going to return it in.
There's a lot of that going on, Lily.
Yeah.
Good for you. Right. Anybody else?